Hi everyone. Let's take a look at this radioactive sample of polonium-211. So we know that polonium-211 will undergo a radioactive decay. So we have polonium-211. Due to that large atomic number there, it'll undergo an alpha decay, the release of an alpha particle, and the formation or the leftover, which is lead-207. Sorry. Okay. So while we know the polonium will decay, is there any way to know which one will decay or when they will be? Well, not really. While we all know that these will at some point decay because they're unstable, there's no way that we can tell which one of these is going to and when it's going to. So then how can we know when something's going to decay or not? Well, instead of focusing on just one individual atom, we could just take a look at the sample as a whole. Rather than knowing when one atom is going to decay, we can measure the time when half of the sample will decay. That time is what we refer to as the half-life of a sample. So the half-life is the time required for half of the atoms in a radioactive sample to decay at least one time. So 50% of what we begin with that is radioactive will have decayed, and that is half-life. It is a measure of the time it will take for something to decay. So if we have, again, the sample of polonium-211, after one half-life, 50% of that will have decayed. And in this case, it will decay into lead-207. 50% of that will still remain undecayed. That is what the half-life is telling us. Now this new sample, once again, half is going to decay over another half-life. So we have a second half-life. So now that it's decayed, that half of a half is now added. So 75% of the original has now decayed because it is half of that 50% that hasn't. And 25% will still remain undecayed. This process continues over and over and over again. And then again, the remaining here, half of this will decay over a third half-life. So now half of that 25% of the original has decayed. So we have 87.5% of the original that is now decayed at least one time. And 12.5% of that original is still undecayed. So the half-life is just the amount of time it took for half of these radioactive atoms to decay, and it'll just keep repeating over and over and over again. So here we started off with 8 radioactive atoms, then we were down to 4, and then 2, and then 1. We knew the time it took for each one of these decays, we would call that time the half-life. So when discussing the radioactive nuclides, the more stable a radioactive nuclide is, well, the longer it's going to take for it to decay. That half-life is going to be longer because, relatively speaking, that nucleus is a lot more stable than some of the other ones. While it's still radioactive and going to decay at some point, if that nucleus isn't prone to decaying as rapidly as the other, it is more stable. Now, for a nucleus that's less stable, that half-life is going to be short. It could even be fractions of a second because it is less stable, it is less likely to be held together as opposed to another radioactive nucleus that's comparably more stable. So half-life is very subjective. It depends on the atom and the isotope itself. They can range from fractions of a second to thousands and thousands of years long. It really depends on what it is that we are measuring the half-life of. Let's suppose that we have 100 grams of radon-222, knowing that the half-life of radon-222 is 3.8 days. So starting off with 100 grams of radon-222, after 3.8 days have passed by, which is the half-life, we'll have half of that amount. So we'll have 50 grams remaining. So that's if one half-life has passed by. Of that 50 grams, another 3.8 days will pass by, and we'll have half of that. So we'll have 25 grams of radon-222. So a second half-life has just gone by. Every 3.8 days, another half-life will occur. So now our 25 grams, that's still radioactive, it's going to undergo another 3.8 day period, so another half-life. Now we have 12.5 grams of radon-222 left after a third half-life. And we would repeat and continue as many times as needed. So the half-life really is just the amount of time it takes for us to have half of what we originally began with. Now, we can't tell which atoms specifically will decay. All we know is that at some point they will, and that by the time half of it is decayed, a half-life has passed by. Phosphorus-32 has a half-life of 14.3 days. We want to know how much phosphorus-32 is remaining after 57.2 days if we originally start with 4 grams of it. So our half-life of 14.3 days tells us that every 14.3 days, half of our sample will be gone. Now we're starting with 4 grams of it, and we want to know how much is left after the 57.2 day period. So we're starting with 4 grams of phosphorus-32. Now after 14.3 days, a half-life will pass by, meaning we're going to have half of that 4 grams. So we have 2 grams of phosphorus-32. Now we're looking for how much is left after 57.2 days. Only 14.3 days have passed by, so we need to wait even longer. So now our 2 grams that has not decayed yet is going to undergo another half-life. So our 2 grams of phosphorus-32 will experience another 14.3 days. And now we have 1 gram of phosphorus-32 left. Again, we're looking for 57.2 days. So we've had 14.3 days and another 14.3 days. Well, that's just 28.6 days. We need to keep on going until we hit that 57.2. So now our 1 gram of phosphorus-32 is going to decay over another 14.3 day period. And now we have half a gram of phosphorus-32. Every single time we are dividing our quantity by 2 because a half-life means that we are just losing half of it. The time period we can see here of 14.3 days is just how long it's going to take. It's not the quantity, it's just the amount of time it takes. The quantity is always being divided by 2 here because we are always losing a half. Now we have an additional 14.3 days added after our 28.6 that have just passed here. So we're at 42.9 days. Still not yet at 57.2. So our half gram of phosphorus-32 is going to decay. Again, another 14.3 days. And now we have 0.25 of a gram, so a quarter of a gram here of phosphorus-32. So now let's add on another 14.3 days that have passed by. And now we see that we have reached 57.2. So after 57.2 days, 0.25 grams of phosphorus 32 remains. And we're just compounding this time here. That radioactive sample will continue to decrease by half after every half-life period. You saw in the previous example that the radon 222 had a half-life of 3.8 days. The phosphorus 32 had a half-life of 14.3 days. It is very relative to whatever it is that we're talking about. If we're taking carbon 14 as an example, this has a half-life of 5,720 years. Okay, so this half-life will really depend on the kind of isotope we have. All we know that at one point it will decay, but sometimes it can take thousands of years or it can take a fraction of a second. So in this case, we're just adding together the time periods that keep passing, and with our quantities halving after every single half-life until we finally get to the amount of time that passed here. So in this case, our 4 grams after 4 half-lives ends up being just a quarter gram left. Life is just taking half a numerous amount of times. We can actually derive an equation for this. Let's use the example that we just did with the phosphorus 32. So if we have 4 grams of that phosphorus 32, we just saw that it underwent a decay 4 times before reaching to that final quantity that we're looking for. So it underwent a change of half 4 separate times, where that quantity just kept getting halved over and over and over again 4 times. So that 4 grams multiplied by half repeatedly until we got to our 57.2 day time period. Well, if we rewrite this here, just knowing what we know about multiplication and exponents, our 4 grams times a half 4 times, that half being multiplied by itself 4 times is equivalent to 1/2 to the power 4. So if we now take advantage of what we know about exponents, we get that 1/2 to the power of 4 becomes 1 to the 4th over 2 to the 4th. Well, 1 to any exponent is going to be 1. 4 times 1 is 4, so this ends up being the 4 grams that we began with times 1 over 2 to the 4th. So if we check this out here, we have 4 over, well, 2 to the 4th is 16. Well, that's 0.25. 4/16, it's just 1/4, which is exactly what we got in the end. So let's take a look at some of the things that's actually involved in our simplified equation here. This 4 grams, well, that's how much we started with. We know that half-life is always dividing by 2. But then let's see this 4 here. What does that 4 represent? Well, that 4 came from the fact that 4 grams was multiplied by half 4 times, and it was multiplied by half 4 times because there were 4 half-lives. So this 4, we can say, represents the number of half-lives. So now if we take these numbers that we actually know the meaning to, and rather substitute them with with variables, it's possible to derive an equation for the half-life here. And in the end, we ended up getting a final amount. So this right here was our final amount. So we can say that our amount after a certain time, t, well, that's going to be equal to our starting amount. So we're going to use A for amount. T is the amount of time that passes by. So AT right here, this is the amount that we're going to have after a certain time t. Well, our starting amount would be when t equals to 0. So our a of 0 would be how much we start with. Because we're dividing by 2 since it is half-life, and that 2 is just going to be raised to the number of half-lives. So we're going to use n for that. So here we have a general equation for half-life. And again, our AT, our A of t here, that is equal to our final amount. So whatever mass unit we're using here, or quantity, we'll make sure to keep that unit. Our A of 0 is our amount at time 0, so basically what we're starting with. Half-life again is always divided by 2, and n is going to be our number of half-lives. So how many times did this decay? And then we can actually rewrite our n. Since going back here, we saw that our n was 4 because we knew that we wanted 57.2 days to pass by, and each half-life was 14.3 days. Well, it's not a coincidence that 4 half-lives passed by, and 57.2, the time that passed, divided by 14.3, the time of a half-life, is 4. So using this information, we can say that the number of half-lives is equal to the time that has passed over the time of one half-life. So with this equation, if we know how much time passed, the time of a half-life, or the number of half-lives, along with an amount that we're starting with, we can then easily calculate the final amount here. So we have derived an actual equation for the half-life in terms of our final and starting amount and the number of half-lives that have passed by.